Welcome back after the ad break, and let's continue with the South Atlantic anticyclone or high pressure system. Now we've already established, we looked just before the break, the anti-clockwise direction of air, as you can see over there. Now over there they're experiencing onshore flow because of the anti-clockwise circulation. Over there, onshore flow. Now very importantly over here, there's two synoptic charts that was drawn. Why do we experience the mid-latitude cyclones only during winter? The reason for it is because during the winter, as you can see, this high pressure system migrates north. So that gives the opportunity of mid-latitude cyclones affecting the Western Cape province. Now what happens during summer? This whole anticyclone, South Atlantic anticyclone, migrates south. So what happens? Mid-latitude cyclones can't have an influence on South Africa's climate during the summer. Now if we quickly look at the South Indian high pressure, the basics, exactly the same principles as the South Atlantic anticyclone. Where does it form? Over the South Indian Ocean. Now keep in mind, what's the difference between the South Atlantic anticyclone and the South Indian anticyclone is the ocean currents. On the west coast is a cold ocean current known as the Benguela, and on the west coast we have the warm ocean current, namely the Mozambican current. Now what does it create? It creates onshore northeastern winds on South Africa's east coast. Why? Because of both of them are high pressure systems as anticyclones. It's an anti-clockwise circulation of air taking place. And the reason, as you can see, because of the reason for it is because it's in the southern hemisphere. Now with the onshore flow, what happens over here? Instead of cool, dry conditions like the South Atlantic high pressure system, this creates warm, moist conditions where the onshore flow is taking place. Why? Because it's moving over that warm ocean current. Now, it also migrates towards the northwest during the summer, winter, and moves southwest during the summer. Southeast. Now if we quickly have a look at over here, as you can see, there's the onshore flow. Why do we experience the onshore flow? Very importantly, the onshore flow that will be experienced will be warm and moist conditions. Why? Because this high pressure system moves over this warm ocean current. The offshore flow will be dry because the air is coming from the interior. Now during the winter, as you can see, the position of it has moved slightly to the north, and during the summer, this whole system also migrates towards the south. Now please pay attention to the anti-clockwise circulation, and obviously during the summer, this South Indian anticyclone is the reason why we experience most of our rainfall during the summer, because this anticyclone is the reason we receive moist air for the formation of rainfall during the summer, which we will explain in the next section. Then we have the last but not least, the Kalahari high pressure system that's over the interior of South Africa. Now, when we talk about the Kalahari high pressure system, its biggest influence on South Africa's climate is during the winter. The subsidence of the Kalahari high pressure, the sinking of the Kalahari high pressure is not as strong during the summer months as in the winter months. The Kalahari high pressure increases in strength, stronger subsidence during winter because of colder temperatures. Now, it creates an inversion above the escarpment and below the escarpment. And because of the Kalahari high pressure, when it's absent during the summer, it means we can experience rainfall. But during its presence, during the winter, we only experience clear blue skies because of the strong subsidence that the moist air can't reach the interior because of this descending air, and it heats up adiabatically. Now, if you look at the winter, like I've mentioned, there's an inversion layer. Now, what do we know about the inversion layer? It's an increase of temperature with an increase of altitude. Okay, so that means it's not normal. Once we go up, what happens with the temperature? It's decreasing. That's normal. When I go climb Kilimanjaro, what's going to happen with the temperature? It's going to decrease. But with inversion, as soon as you're moving up in altitude, the temperature increases. Now, the best way to explain this Kalahari high pressure is in my following two diagrams. They are on this page, but I would rather draw them myself, and I'll quickly do it. Now, first of all, I'm going to draw a diagram that represents summer. Now, this is the plateau and the escarpment. Now, basically what happened, like I've mentioned, the Kalahari high pressure is not as significant during the summer month, and it's got a weak subsidence, means not very strong. So the inversion, as you can see, is above the escarpment. Now, what do we experience during summer? We experience really warm conditions. Now, with warm conditions, what does air do? It rises. Now, with the warm moist air coming in, ridging in, onshore flow from the South Indian high pressure, this warm moist air can reach the interior, it can rise, and it can cool, condense clouds and rain. And that's the reason we experience rainfall during the summer. But during winter, because of colder temperatures, what happens? The Kalahari high pressure has got a stronger subsidence, meaning a stronger subsidence, meaning the air is sinking. Why? Because of colder temperatures. Now, over the interior on the plateau, because of the sinking air, what do we experience? Clear blue skies, only sunlight. The reason why we experience this clear blue skies is because the inversion is below the escarpment. This moist air coming from the South Indian anticyclone high pressure system can't rise. It can't move over the escarpment. It's blocked by the inversion layer. So that means no moisture can reach the interior of southern Africa because of the Kalahari high pressure system. The system, because of the sinking air, it blocks this warm, moist incoming air from the east coast and do not allow the warm, moist air to reach the interior. Now, as you can see over here, this is during winter months. As you can see, June over there, there's the Kalahari high pressure. It's anti-clockwise circulation. That's sinking air. So basically what happens over here, this warm moist air coming from the South Atlantic, moving over the Mozambique current. Because of this strong subsidence over here, this warm moist air cannot reach us in the interior. So that means no rainfall. And if we look what happens during summer, as you can see, now this is also June. Let me just try and find during summer. See, it's the same diagram. What happens during summer? The subsidence is much weaker. This inversion layer is over there. So that means this warm, moist air may reach the interior. It will eventually rise, it will cool, and it will create rainfall. Now, the type of rainfall that we experience during summer over the interior is known as line thunderstorms. Now, line thunderstorms develop only during summer when there's an extensive area of low pressure over the interior. Now, what do we know about low pressure? It's rising air. Now, why do we experiencing it during summer? Because of warm conditions. Low pressure systems develop over the interior of southern Africa because of very warm conditions, because it's summer. Now, by now, you've learned that air moves from a high pressure to a low pressure. In this case, the Kalahari high pressure, like we've mentioned, is not really present in the winter, during the summer season of southern Africa. It had migrated towards the north. But the South Atlantic and the South Indian anticyclone are very much there. And as we know, because of the onshore flow, air moves from the high pressure system to the low pressure system, from the high pressure to the low pressure. Very importantly, we have a warm ocean current over there, and we got a cold ocean current over there. Now keep in mind, we have anti-clockwise circulation taking place. This air moves from the high pressure to the low pressure, and that is cool, dry air. And from the other side, we have the South Indian, the high pressure system. We're experiencing onshore flow, creating warm, moist air. Now, air moves from a high pressure to a low pressure. Now, immediately what develops over here is known as a moisture front. Now, grade 12s, you've learned what a front is in the previous lessons. What's a front? It divides two masses of air. In this case, this moisture front divides the cool, dry air coming from the South Atlantic high pressure that flows into the low pressure system, and the warm, moist air coming from the South Indian anticyclone flowing to the low pressure system. There's a difference in moisture because on the one side we've got cool, dry air. On the other side we've got warm, moist air. And this moisture front, this whole system moves from west to east. So what basically happens? The cool, dry air is much heavier and denser than the warm, moist air. So what does it do? Almost similar to the mid-latitude cyclone. As the system progresses, what does the cool, dry air do? It forces this warm, moist air to rise. It cools, condenses, and formation of clouds, and eventually will lead to rainfall. If we look at berg winds, it's kind of self-explanatory. Berg winds is the name, it means berg is mountain in Afrikaans. So what do we know as wind? Wind is when air moves from a high pressure to a low pressure. So in theory, what can we say? It's mountain winds. It's when the air blows from the mountain down an area or up the mountain, vice versa. Now, berg winds happens usually during winter times, or can happen during summer times, but is more prominent during winter times. During winter, we can experience, if you look at the diagram over here, that the South Atlantic, South Indian high pressure ridges in over the western side of southern Africa. Now you know, because it's an anticyclone, it's anti-clockwise circulation. And a mid-latitude cyclone is a low pressure system. And what do you know? Air moves from a high pressure to a low pressure. And if I had to draw a cross section from, let's call this point A and this point B. This is what it looks like from point A to point B. There's point A, there's point B. So the air moves from the high pressure system to the low pressure system. Now what happens? As you can see, in the top diagram, this is over the interior on the plateau. This is down at the coastal regions. What do we know in altitude difference? We are much higher over there than over there. And what do we know with altitude? Temperature decreases with altitude. Now, I'm going to use my example again. I'm climbing Kilimanjaro, the temperature is decreasing. Now, once we reach the summit, what are we going to do? We're going to climb down Kilimanjaro. What's going to happen with the temperature? It's going to increase. So the air moves from the high-lying area down to the bottom area. And what's going to happen with this temperature? It's going to increase. And we say this temperature increase adiabatically. Very importantly, because instead of the temperature decreasing while we go up, it's decreasing because we're coming down. In this case, because the air moves from the high pressure down to the low pressure, down the escarpment, creating uncomfortable warm conditions. Now, grade 12s, these berg winds can create some havoc. We've seen it in 2017 during the Knysna fires. So we need to be especially take precautionary measures when berg wind conditions may prevail. Because of the area that's constantly dry, because it's dry season, if we're not being careful with open fires, we can cause major destruction to crops and farmland. Thank you for watching. See you next time.